we shall start our discussion today on the reheating and regenerative cycles. We have discussed in the previous class about the modification of Rankine cycle essentially to increase the efficiency, that is the efficiency of the Rankine cycle. Now, what we have seen from yesterday's class is that one way to increase the efficiency of the ideal Rankine cycle is to increase the boiler pressure or to increase the temperature of steam leaving the boiler, that is to superheat the steam. So, these two methods, if we increase the increasing boiler pressure or superheating the steam. Okay. So, we have seen that whether we try to increase the efficiency of the cycle by increasing boiler pressure, we have seen maybe we can increase the efficiency by 3 to 4%, but at the cost of that increase in efficiency we are going to invite another problem of having high moisture content of steam at the exit of the turbine. So, this is having leads to high moisture content of steam leaving the turbine. So, this is one important drawback. For superheating the steam, we have seen that we can increase the efficiency, but we also can increase the moisture content. I mean we can increase the quality of the steam at the exit of the turbine. Now, superheating the steam, by superheating the steam beyond 0.3, I mean if we try to draw the TS diagram, we have seen that so, if we increase the temperature of steam beyond 3, that is I mean just not the saturated vapor, if you would like to have superheated vapor by increasing steam temperature, by how we can do, we can discuss that we can allow steam to pass through the superheater. So, we can really increase the quality of the steam at the exit, but the question is maybe we can increase the efficiency, also the quality of the steam leaving the turbine can also be increased, but the problem is the turbine material consideration. So, material consideration puts a restriction on the degree of superheat, right. So, we cannot increase superheat, I mean we can increase or we can increase the temperature of steam beyond 0.3, but the degree of superheat by which the steam temperature can be increased is not arbitrary. So, we have constraint that is imposed by the turbine blade material. So, that is I am writing blade material. Okay. So, considering these two aspects, you know that we have discussed about simple as ideal Rankine cycle, and we have also discussed about these two important issues by which we can really I mean increase the efficiency of the simple Rankine cycle. There is also another way by how we can increase the efficiency of the simple Rankine cycle is by lowering the condenser pressure, but that aspect we will be discussing when we will be discussing about condenser. So, now I mean we can reduce the condenser pressure, but we cannot even go beyond a particular value, that we will be discussing. So, for the time being at least we should know that I mean we really cannot increasing boiler pressure, or we really cannot increasing the temperature of steam leaving the boiler to the extent possible. We are having restriction considering the blade material of the turbine. Now, so these are not the viable solution. So, basically you know that I mean considering this aspect, that is material aspect, the constraint imposed by the turbine blade material, also the moisture content of steam. Another important method is reheating. Reheating the steam, this is called reheat cycle. So, this is again very simple. Let me write the issue is what we can do. We can reheat the steam. So, basically reheating the steam, it is accomplished by increasing boiler pressure. So, basically it is utilized, it is utilizing high boiler pressure and superheating. So, from the previous discussion we have seen that increasing boiler pressure also leads to increase in efficiency, but it leads to the, or it deteriorates the, it leads to the deterioration of the quality of the steam leaving the turbine. Superheating also leads to increase in efficiency, but as I discussed that from the perspective of the turbine blade consideration, we are having even some kind of restrictions. So, now we can use the combination of these two, that is high boiler pressure as well as superheating the steam to increase efficiency, and that is nothing but reheating. So, the concept of reheating which I have written over here utilizes both high boiler pressure as well as superheating, and we will see that utilizing this concept we can increase the efficiency of the cycle by 4 to 5% without compromising the quality of the steam at the turbine outlet. So, now let me draw the schematic depiction and that will help to. So, if I draw the schematic depiction, say I will be drawing over here. So, here you are having boiler, let me write here boiler. So, we are having boiler, in fact it is very, so I am writing, I am trying to draw over here. So, this is boiler. So, heat input. Now, so we are trying to utilize the concept of high boiler pressure, that is combination of high boiler pressure and superheating the steam, essentially to increase the efficiency of the cycle without compromising the quality of the steam. To implement that, what we need to do? We need to expand steam in two different stages. So, I mean if we try to utilize, so let us erase this line, and if we try to, so this can be made possible by expanding stream in two stages. So, that means we are now trying to expand steam in two different stages. What is done? So, this is high pressure turbine HPT and two stages of turbine. One is high pressure turbine that is HPT, and another is low pressure turbine that is LPT. Okay. So, essentially that steam which is coming out from the boiler will be allowed to pass through two different turbines. First one is high pressure turbine, and then after doing work, when steam is expanded in the high pressure turbine, it will steam, the work which is done by steam will be taken, after doing work in the high pressure turbine, that steam will be taken back to the boiler. So, after doing work, the steam will be taken back to the boiler and it will be allowed to pass through a coil which is placed inside the boiler, and then again the steam will be taken to low pressure stage turbine. So, this is low pressure HPT and this is LPT, and finally, we will be getting work output from the turbine, and this steam will be taken to the low pressure stage turbine, and finally, when the steam is coming out from the low pressure stage turbine, it is taken as usual to a condenser, and so this is condenser, and from the condenser the collected condensate is pumped back to the boiler. So, this is what is the schematic depiction. Say if I give name, this is 1, this is 2, this is 3, this is 4, this is 5 and this is 6. So, here the concept is, so basically we are getting W out from here and this is Q out, and we need to give W in over here. So, this is the concept, you can see. So, as I told you, steam will be allowed to expand. So, we will be using superheating steam. So, we will be using superheated steam while it expands in the high pressure stage turbine. So, the steam which is coming out, so boiler will be operated at high boiler pressure, and also the steam which will be coming out from the boiler is the superheated steam, not the saturated steam. So, when steam is expanding in the high pressure stage turbine, it does work on the rotating part. See the rotating part. So, basically the wheel, a turbine shaft, we have a common turbine shaft. So, the shaft of the high pressure and low pressure stage turbine is common. So, they are connected together. So, now after expanding, steam is taken back to the boiler, we are having one reheating coil. So, here, so this is known as reheating coil. So, this is called reheating coil. So, the name reheating is coming from the fact that after expanding steam, after doing some work in the high pressure stage turbine, steam is taken back to the boiler, wherein it is allowed to pass through this reheating coil. So, basically it is passed through a coil where it is reheated. So, that is why the name reheating is coming. Now, after this heating, again steam is taken to the low pressure stage turbine and it does work again, and finally, the process is as usual that we have discussed many times. So, question is, if we do this practice, perhaps this is the this is very common practice which is followed in modern steam power plants. We can increase the efficiency because the first of all boiler is working at the high boiler pressure. So, it is high pressure stress turbine and low pressure stress turbine. Now, question is, let us briefly draw the TS diagram which will help us to understand. So, if I draw the TS diagram which will help us to understand the increase in efficiency without compromising the quality of the steam in a more convenient way. So, if we try to draw the TS diagram. Okay. I will be using different colors to represent different processes. Say, I mean now if we go back to the previous slide. So, you understand process 6 to 1, that is the condensation process. So, we will be having two different pressure, one is boiler pressure, other is the condenser pressure. So, now if we go here, say we are having condenser pressure. So, this is constant pressure line in TS plane. So, this is P condenser. Okay. Now, so this is P condenser pressure. We will also have one pressure line, that is boiler pressure line. So, this is, say this is P boiler. Okay. So, as I told you that if I give name, so if I go back to the previous slide wherein we have tried to describe the processes, all the processes through the schematic depiction. Process 1 to 2, that is reversible adiabatic process, work done, that is nothing but minus VdP. In fact, again I am telling, for both the reversible adiabatic and reversible isothermal processes, the work done is minus VdP, it is not PdV work. So, the process 1 to 2, that is pumping process, that is here. So, this is 0.2 and this is 0.1, right, reversible adiabatic process, that is isentropic, right. Now, steam, the boiler is operating at the high boiler pressure and steam is reheated. So, it is not the 0.3. So, if I give the name this point, say 3 prime, or I am giving name something, say A. So, this is, say this is point A. So, the point A is the saturated vapor, but it is not, because we will be utilizing the concept of superheating as well. So, the boiler is operated at a relatively high pressure, also we are allowing steam to, we are allowing the temperature of steam to increase beyond point A, that is we are trying to have superheating. So, say this is the point. So, this is point 3. So, this is point A. Now, when steam, if 3 is the temperature, this thermodynamic state point 3, now steam is taken to high pressure stress turbine and it does work. So, when steam is entering into the high pressure stress turbine, it will expand up to an intermediate pressure, right. So, when steam is expanding in the high pressure stress turbine, after expansion, after it does work on the rotating part of the turbine, it is taken back to this coil for reheating, right. So, it is expanded up to an intermediate pressure, right. This is expanded, say isentropically, right. So, it is isentropically expanded up to this intermediate pressure, right. So, high pressure stage turbine to the same intermediate pressure. So, say this is point, what I have given the name. So, I have given name 4. So, this is 4 and then steam is reheated. So, after this expansion if I give the name, say this is 0.4, right, say up to this intermediate pressure, I am trying to draw using different color again, say this is up to the intermediate pressure, we really do not know, maybe this is an intermediate pressure, right. So, right. So, up to this 0.4 stream is expanded, if I use again red color. So, this is expanded. So, this is 0.4, right, and then steam is reheated again inside the boiler, but the expansion takes place up to an intermediate pressure, and when steam is taken back to the boiler and it is allowed to pass through this coil. So, the pressure is not the boiler pressure, but somehow it is a pressure that is it is an intermediate pressure. So, say up to this, and then the steam is heated preferably up to that superheat temperature. So, I will be, so this is 0.5, right. So, this is 0.5. See, at 0.5, the 0.5 is the inlet state of steam before it enters into the low pressure stage turbine. So, the temperature of 0.5 is preferably equal to the temperature of 0.3, otherwise it will not be justified. So, when steam is taken back to the boiler and it is allowed to pass through this heating coil, it is reheated rather, it is reheated up to the temperature which is equal to the temperature of steam before it enters into the high pressure stage turbine. So, basically T5 is, it is designed in such a way that T5 should be equal to T3, but it is heated up to an intermediate pressure. So, this is 5, so this is 5, and then it is expanded in the low pressure stage turbine isentropically. So, this point is 6 and this temperature is constant. So, T5 equal to T3 equal to constant, right. So, what we can see, I mean if we try to understand that we are utilizing high boiler pressure essentially to increase the efficiency, we are also allowing steam temperature to go beyond point A, that is we are superheating. Now, if we superheat and also we are using high boiler pressure, the concept of these two we are utilizing over here, but if we allow the steam from 0.3 isentropically, so this is 0.6, so I am writing. So, this is 0.6. If I allow the steam to expand isentropically from 0.3 without reheating, then say if I give the name 0.4 prime, try to understand, if we do not increase this reheating stage and if I allow steam to expand from 0.3 isentropically, then the quality of the steam will be X4 prime. Now, quality of the steam is X6. So, definitely X6 is greater than X4 prime, right. So, though we are using high boiler pressure, but still we are not going to compromise the quality of the steam by how? By incorporating this reheating stage. So, by the reheat stage, quality of steam becomes higher, also the reheating increases the efficiency. Okay. So, this is what we wanted to discuss. So, see, only by having one reheat stage we can increase the quality of the steam. And you also can see the total area. See now the total area under the process line 2, 1, 2, 3 prime, 4, 5, 6, 1 will give the net work output. So, this is the total work output, you can see, right. Had steam been allowed to drop to expand isentropically from point 3 to 4 prime, we had to compromise the work done that I can show by this hatched portion, say this is the extra amount of work that we are getting. So, we can see the area shown by the hatched, this hatched portion shown by this green color is the additional amount of work we are getting. Not only that, because of this extra amount of W net, cycle efficiency will increase, we also can improve the quality of the steam leaving the turbine. So, a single reheat stage increases efficiency by 4 to 5%, right. So, now if we consider this reheating cycle, so basically it is now commonly followed in most of the modern power plants. So, by single reheat we can increase efficiency by 4 to 5%. So, by single reheat efficiency increases by 4 to 5%. Okay. So, you can say that we can increase the number of reheat stage more than 1. Again let me talk about. So, see what is done, let me tell you. Steam is, boiler is operating at high boiler pressure, at high pressure. Steam is superheated up to point 3, beyond point A. Steam is taken to the high pressure stage turbine and it is allowed to expand up to an intermediate pressure, that is P5. So, this is the intermediate pressure, P intermediate. So, this is expanded up to an intermediate pressure, say P5, isentropically up to 0.4, and then it is taken to that heating coil and reheated, and that is why the name reheating is coming up to the temperature 0.4. Preferably it is designed. So, the reheating stage is designed in such a way that after reheating temperature should be equal to the temperature T3, that is the temperature which was before temperature of steam when it was at the inlet to the high pressure stage turbine, and then steam is finally expanded isentropically up to 0.6. Now, question is, if we can increase efficiency by 4 to 5% by having only one reheat stage, we can increase the reheat stage maybe more than one, but we cannot. See, question is, you can see that if I try to draw the TS plane, so the concept is here, right. So, say so this is 1, 2, now so we can have say multiple reheat stage, right, and if we can write 6, see you can see multiple reheat stage, but you can see this T average of reheat. So, this is multiple reheat stages, right. So, having a multiple reheat stages, we can increase efficiency maybe more than 4 to 5%, but one problem is that the average temperature of reheat, you know that efficiency of the thermal power of any Rankine cycle or reheat Rankine cycle is nothing but 1 minus TL by TH. So, that is what we have learned from the Carnot cycle, ideal Carnot cycle. So, our objective should be to increase the average temperature or mean temperature of heat addition and to decrease TL. So, now if we increase the average temperature of heat addition, that is TH or TH mean, right, we can increase the efficiency. Now, though if we are trying to have multiple reheat stages, can we really increase the mean temperature of heat addition from the what we can see from the diagram? No. Though we can increase multiple reheat stage, but average temperature of heat addition is remaining almost constant. In fact, that is what I have discussed or I have highlighted, that when steam is reheated, it is designed in such a way that reheating temperature is T5 and the T5 is taken in such a way, I mean it is designed in such a way that T5 will be equal to T3, right. Though, so basically though we can increase efficiency by 4 to 5%, increase in efficiency by 4 to 5% only having on one reheat stage, but multiple reheat stages will not increase efficiency in that proportion, because the average temperature of reheating is remaining same and that is the same order of magnitude. Since the average temperature of reheating is of the same order of magnitude as that of the superheating. So, you can understand na. So, basically what I am telling, if we have only superheating up to 0.3, then average temperature whatever we will be having, that is equal to the average temperature even after having one reheat stage. And that is what I was telling you, that it is reheated up to the temperature which is nothing but equal to the T3. So, this is one of the important drawback, that we really cannot go beyond 1 or 2. So, the practical aspect is that we can go up to maximum 2 reheat stages, not more than 2 reheat stages. Why? Maybe we can go up to 3, 4 or 5 reheat stages, but the gain in efficiency even after having 4 or 5 reheat stages will not be justified by the cost associated with having the incorporation of 5 reheat stages. Try to understand. So, we can go up to 5 or 6 reheat stages, there is no restriction, but restriction is there that if we can go up to 5 or 6 reheat stages, then the gain in efficiency out of these 6 reheat stages should be justified from the cost, from the perspective of the cost analysis, cost comparison. So, if we do the cost comparison, so the cost associated with the incorporation of 6 reheat stages should be justified from the efficiency or from the gain in efficiency that we are getting out of this. So, from the practical point of view, it is seen that, so this is mean temperature of heat addition. So, more than 2 reheat stages are not recommended. Okay. So, this is very important, that it is essentially from the cost comparison or cost analysis. Okay. So, this is very important, but so one disadvantage is that we cannot increase more than 2 reheat stages. So, this is one of the one disadvantage I can tell, but what are the advantages? Advantages is that efficiency increases, number 2, quality of the steam increases, improves. So, these two already I have discussed. The most important part is, see, efficiency will increase, that we can see from the schematic depiction from the TS diagram, that because of the hatched area. Quality of the steam also will increase, that we can see from this TS plane. See, now try to understand one important thing. This much amount of additional work, net work output we are getting for the same steam flow rate, right. So, for the same steam flow rate, because if we go to the previous slide wherein you have depicted the schematic depiction, the steam flow is remaining same. So, if we had say m kg of steam m dot, so m kg of steam at point 3, here also we are having m kg, here also we are having m kg. So, for the same steam flow rate we are getting this extra amount of work. So, from our one of the previous classes, if we try to recall that since for the same steam flow rate W net increases, so SSC will be what? So, this is very important. So, for the same steam flow rate, the work output becomes higher. This aspect signifying a low SSC, specific steam consumption rate, thereby and a smaller plant. Right. So, now question is, which is very important to discuss over here, that in addition of these two features, that is efficiency increases and quality of the steam also improves, we are getting that for the same steam flow rate the work output becomes higher, which is quite obvious that the same mass flow rate of steam we are getting this extra amount of work output. So, it signifies low SSC, specific steam consumption rate, and that is nothing but the smaller plant. If the plant is smaller, operational cost will be less. So, it is also I can say viable from the economical point of view. So, the greater is the plant, higher is the installation cost, greater is the size of the plant, higher is the installation cost, also higher is the operational cost. See, what we can see from today's discussion is that, see, SSC, that is specific steam consumption rate, is low, which is nothing but which signifies that plant is low, plant is small. So, smaller plant. So, smaller the plant, smaller will be the operating cost as well as the installation cost. So, this is one of the very important advantageous feature. Now, one important point I would like to discuss, that we have discussed about that we really cannot go beyond 2 reheat stages, from the practical point of view. As I discussed that you can go up to 5, but it should be justified, right. So, 5 reheat stages, first of all the installation cost as well as the operational cost. So, the cost associated with the installation as well as operation should be justified from the increase in efficiency that we are getting out of these 5 reheat stages. So, having a comparison cost analysis, it is observed that it is seen that more than 2 reheat stages are not recommended. However, now question is, we have discussed in the last class that superheating can also increase the work output, also it increases the quality of the steam. Now, question is, we could not stick to that particular aspect. In fact, superheating really is a very feasible way of increasing efficiency of the Rankine cycle, but only constant is the turbine blade material. So, from today's discussion we can see, if we can have a particular specific turbine blade material which can withstand high temperature, then perhaps superheating will be more viable than reheating stages. So, having even one reheat stage, you can understand so many things. You have to have pipeline, you have to have 2 different stages of turbine, you have to have one heating coil. So, installation cost as well as operational cost, involvement of both operational and installation costs are is there, but question is, if we can have a specific turbine blade material which can withstand high temperature, then perhaps it is not required to go for the reheating method, instead we can use the superheating stage. So, though reheating provides all these favorable I can say features, even then if we can have a specific material which will be used to fabricate turbine blades, and if that particular material can withstand high temperature, then superheating will be more viable than the reheating stage. Okay, so with this I stop here today, and we shall continue our discussion in the next class. Thank you.